Okay. We're going to take a look at some geometric series here. And let's see why this is a geometric series. Now, the first term is A. The second term is AR. We have to verify that the third term is AR squared now. Okay. This is what we're saying. So, if this is geometric, A would be 1/8. AR is negative 1/4 now. Okay, that's a negative value. Replace your A, which is 1/8. So you end up getting the relationship that 1/8 R should be negative 1/4. Now, divide both sides by 1/8, you get negative 1/4 divided by 1/8, which is really negative 1/4, times 8 over 1. What we're saying now is that R is going to be negative 2. All right. So we have all the information we need. We got to verify that AR squared is a positive 1/2 now. So is AR squared equal to positive 1/2? Well, we know A is 1/8. R is negative 2. We have to square that. So we get 1/8 times 4, sure enough, is in fact 1/2. Okay, 4/8 is 1/2. So yes, we have a geometric series now. Now, geometric series converge. We have to verify if the absolute value of R is less than 1. Now, R is negative 2 here. We plug in the negative 2 for R. So what do we see here? That the absolute value of negative 2 is in fact positive 2, and positive 2 is not smaller than 1. So this is a case where the geometric series diverges. So we have a divergent, we'll say diverges. We have a divergent geometric series for question 1. That's divergent because R is negative 2. So we have to check this criteria here. Okay. Question 2 now. Is this geometric? Well, AR squared. We got to verify and find the values of A and R to see if it's the third term now. This means A is 1, AR is 0.4. So 1 times R is 0.4. So the radius value, or I should say just the R value, is 0.4. Let's keep it at that. Now, we got to verify the third term. AR squared needs to be 0.16. So, is AR squared 0.16? Well, 1 times 0.4 squared should be 0.6, which means 0.4 squared, sure enough, is 0.6. That is actually true. Okay. So 0.4 to the second power is 0.6. This means we, in fact, have a geometric series here. The series is geometric. Now, if the absolute value of r is less than 1, which means the absolute value of 0.4, which is 0.4, is in fact smaller than 1. So this is a true statement. We're looking for this relationship. So the sum now is a over 1 minus the r value. And r we know is 0.4. A we know to be 1. So we plug in the values for the sum here. So we get 1 over 1 minus 0.4, which is 1 over 0.6, which is 1 over 6/10, which is 10/6, or better yet, 5/2. So the sum value is 5/2. So this geometric series converges, and the sum is 5/2. All right. Very good. Okay. Extra examples. All right, now let's take a close look to this. Let's do a little algebra here on this. This next one, number 3, if we do some algebra, that looks like it's -6 over 5 now to the n minus 1 power here. So the real series, just by doing a little bit of simplification here, is what we see. Now, let's look at the terms here. If we let n be 1, we get -6/5 to the 0 power. Now let n be 2, -6/5 to the first power, n be 3, and you guys get the picture. N is 1, n is 2, n is 3. We're generating terms of the series, which means this is 1 minus 6/5 plus 36 over 25. The next term is going to be negative, but we only need to look at the first 3 terms again. Because if this is geometric, we know we have A, AR, AR squared now. Okay, so what this means is A is 1, AR is -6/5. Replace this A here with 1, which means R is -6/5. Here's our R value. All right, we got to double check. Is AR squared equal to 36 over 25? That means 1 times -6/5 squared has to be that third term of 36 over 25. Doing some arithmetic, sure enough, we verify that we get 36 over 25. Okay, that means we have a geometric series. The series is geometric. All right. However, we got to check. Is the absolute value of R smaller than 1? That's the absolute value of 6/5 needs to be smaller than 1. 6/5, ladies and gentlemen, is not smaller than 1. 6/5 is like 1 and 1/5, right? As a mixed number. So that is not smaller. It's actually larger. So this is a divergent, this diverges geometric series. Okay, we only have convergence if the absolute value of r is smaller than 1, so this diverges. All right. Okay. Let's take a close look at what this series is. This is under the geometric series questions. By definition, that's 2 over 1 to the nth power here. Let's double check. So the terms is 2 to the first power plus 2 to the 1/2 power plus 2 to the 1/3 power, and this goes on forever. Is this geometric? Well, if it's geometric, we have to verify a few things. Okay? This means a is 2. AR is the square root of 2, 2 to the 1/2. And AR squared needs to be the cube root of 2 now, because that's 2 to the 1/3. 2 times the square root of 2, this certainly is not the cube root of 2. So this series is not geometric. All right. Okay, however, what do we do? I think when we looked at the series here, let me go back to our notes. We had ended with an important concept called the test for divergence. If the limit of an is not 0 or does not exist, then the series diverges. So that's going to give me a nice hint. The limit is not 0. So let's take a look at this here. This is going to be our an. So the limit as n goes to infinity of an is the limit as n goes to infinity of 2 to the 1 over n. Now, as n goes to infinity, 1 over n goes to 0, and 2 to the 1 over n goes to 2 to the 0, which is 1. What we've found is that this limit is not equal to 0. In fact, the limit is 1. So I can just say this. The limit equals 1. It is not 0. So the series will diverge by the divergence test. So they snuck this in. This diverges by the test for divergence, also known as the divergence test. So they snuck it in, ladies and gentlemen. It's good to know. But it's certainly not geometric. So this is kind of the process that you would go through in general. And this is a geometric series, but it involves a variable x here. Let's look at these terms here so I can show you guys what I'm talking about. When n is 1, we have the power 1 there. X minus 4 squared, x minus 4 cubed, and this goes forever. Now remember, geometric series looks like this. well, it's a geometric series here. If we simplify this first term, we get x minus 4 plus x minus 4 squared plus x minus 4 cubed, and so on. It looks like yeah, that's what's going on here. It looks like the tip is having an issue. AR squared. So if you check if this is geometric, you're going to find the following here. A is x minus 4. AR x minus 4 squared. So that means x minus 4 times r becomes x minus 4 squared, and r is x minus 4. Solving for r here. Okay, solving for this. Don't forget, this is my a value. Okay. And so we're going to have convergence now. This is in fact geometric. You say, how do we know? Because AR squared will be x minus 4 times x minus 4 to the second power. That's really equal to equal to, this is going to be AR squared, x minus 4 to the third power. So it does check out. Jeez. Okay, if the absolute value of r is less than 1, we have convergence. And r, by the way, is x minus 4. So what does this mean? It means the absolute value of x minus 4 needs to be 1. This is an absolute value inequality. It means x minus 4 is between -1 and +1. We can solve for x by adding 4 to the left, the middle, and the right. We get 3, ladies and gentlemen, is less than x, which is less than 5. So we're going to get convergence here for these values of x. But what is the sum going to be? Okay? The sum, let's remember that S is A over 1 minus R. A is what? X minus 4. So here, replace it with an x minus 4. R we found out was also x minus 4 over here. So just doing a little arithmetic, we get x minus 4 over 1 minus x minus 4. The sum's going to be x minus 4 over 1 minus x plus 4. Your sum's going to be x minus 4 over 5 minus x. Geometric series with the variable x. All right. So this equals x minus 4 over 5 minus x for 3 less than x less than 5. Okay, this is what they're looking for. This is what the sum is. It converges for these values of x. It's a geometric series. All right. Is this a geometric series? The answer is yes. You're going to find out, ladies and gentlemen. The first term, x minus 3 to the first power. The second term, x minus 3 squared. The third term, x plus 3. This is AR squared. A is x plus 3. R is another x plus 3. AR squared will check off. Now, if the absolute value of R is less than 1, what does that mean? We're looking for the absolute value of x plus 3 being less than 1, which means negative 1 less than x plus 3 plus 1. If I subtract 3 from the left, the middle, and the right, we'll get negative 4 here, less than x, less than negative 2. Let's write that a lot better. Negative 4, this is what the iPad does. It wants to do this. Come on. Negative 4, less than x, less than negative 2. I guess we have to write slower. We'll get convergence for these values of x. Now the sum, s, has to be a over 1 minus r again. So it means our sum needs to be x plus 3 over 1 minus x plus 3. Just using a little arithmetic, little algebra, distribute. The sum's going to be x plus 3 over, looks like it's going to be 1 minus 3, negative 2 minus x. Anyway, we'll just keep it like that. So we converge to this particular sum for these values of x. All right. Number 7 now. We could do just a little bit of algebra here in number 7. So we have x minus 3 over 2 now, raised to the nth power. So we're looking at the series here. 1 to infinity. All right. Let's look at the terms. X minus 3 over 2. X minus 3 to the 2 to the second power. Third power, and that goes forever. AR squared. You're going to find that this is geometric, where the A term is x minus 3 over 2. The R term is x minus 3 over 2. So this is going to be a geometric series. Okay? You'll get convergence for the absolute value of r being less than 1, which means the absolute value of x minus 3 over 2 needs to be smaller than 1 for convergence. All right, properties now. X minus 3. There's our iPad game again. Let's go up here. X minus 3 and absolute value over 2 needs to be smaller than 1. I can solve for the absolute value by multiplying both sides by 2, and then 2 times 1 is 2. An absolute value inequality, by definition, negative 2 x minus 3 is less than positive 2. So we can add 3 to both sides. And in fact, it's the left, middle, and the right. You'll get convergence for values of x that are between 1 and 5. You're going to get convergence here. Okay. The sum, if we look at that, what it'll converge to? A over 1 minus r. Well, A is x minus 3 over 2 over here. R is the same thing. So there's going to be some algebra here. X minus 3 over 2 over 1 minus x minus 3 over 2. All right. Still a little algebra here. X minus 3 over 2 over 2 minus x minus 3, everything over 2. 2's cancel. The sum is x minus 3 over 2 minus x plus 3, because we're going to distribute that negative sign. So your sum will be x minus 3 over 5 minus x. So we're going to get convergence to this particular sum depending on the values of x, where x needs to be between 1 and 5. All right, geometric series. Okay, now let's look at the... all right, let me double check a few things here for you guys. All righty, so, okay, so ladies and gentlemen, we were working with series the last we met. I'm going to send you guys still some more of those geometric convergence series when I get a chance. Couldn't do it this weekend, but okay. So here is an example of a series. I want to say a few things about it, though. The series is not geometric. Okay, and you might say, well, how do we know that this particular series is not geometric? Because if you look at the terms of the series, you start with n is 2, by the way. And so the first term will be 2 minus 1 plus 1 over 3 minus 1, okay, plus 1 over 4 minus 1. That will go on forever. This is when n is 2, n is 3, n is 4. So I'm going to remark that this is really 1/2 plus 1/6 plus 1/12. Okay, do you guys see my point? Start again with n is 2, n is 3, n is 4. Now, if this series was geometric, this will be AR squared. So let's go through the process, right? You guys remember the process here. That we're going to look at the first two terms and verify the third term to see if that is in fact geometric. So, all right, here we go. A is 1/2. AR is 1/6. So, what does that mean? That would mean 1/2 R equals 1/6, because that's in fact what A is. Is that right? And so my R value is 1/6 divided by 1/2, or R would be 1/6 times the reciprocal. R is going to be 1/3 now. Okay, so here's our R value now. So using that information, we got to verify now, is AR squared equal to 1/12? And we have what? 1/2 times 1/3 squared is 1/2 times 1/9. That's 1/18. So, ladies and gentlemen, this is not at all what's the story. Yeah, that is supposed to be 1/12, okay? So, AR squared, we know, is supposed to be 1/12 and cannot be 1/18. There's the issue. So, what does that mean? This is not what? Geometric. Take a good look at this, okay? So, you do not have a geometric series. This is the first example that you see in this section, chapter 12.2, where you don't have a geometric series. All righty. And then the question is going to be still, does this series converge or diverge? And of course, if it converges, they want the finite sum. So sure enough, we know the terms are not geometric. And the only other tool we have now is what? Do you guys know? You guys are working on this over the weekend, I hope? So what's the deal here? What do you do? Well, you have to consider what? What do we see as the mechanism last week for all of this? What's under the hood? Consider the what? Sequence of what? Partial sums. Okay, you're going to look at that sequence of partial sums. And hopefully that sequence will converge to a value, right? You got S1, S2, all the way up to Sn, the sequence of partial sums, where really S1 we know is, well, we can't call it 1 in this case. It's going to start at what? 2. Is that right? I mean, it is the first term, but really this is how we kind of define Sn. You start at 2 and you end at n, and maybe wait, I'm going to do something here. Yeah, I guess we'll do it this way. Capital N. 1 over n, n minus 1. So this will be a capital N. It doesn't have to be, but all right. So sequence of partial sums is really defined to be now 1 over 2, 2 minus 1 plus 1 over 3, 3 minus 1. It is, but this is what I want to say to people here. Okay, let's take a closer look at what you have here. This is a rational function. I'm going to use PFD. Does anybody want to remind me what is PFD? What do we abbreviate PFD with? Partial fraction decomposition. So you want to use partial fraction decomposition here, and I'll show you why. Okay. If you don't, you're going to get that those terms that I started to write down. Now, by partial fraction decomposition, this portion here is really 1 over n minus 1 minus 1 over n. So our sequence can be written this way. Okay, and that's all because of partial fraction decomposition. Now, what this is going to do for us is going to be very meaningful. So we start with a series. It's not geometric. It's a rational function, and we use partial fraction decomposition. This is going to be your fundamental example of what we call a telescoping series. Okay, that's the first example in any book on telescoping series. Now, they call it telescoping because what's going to happen is that your terms will collapse. So you get terms will collapse. This is why we call it a telescoping series. Collapsing terms is what they should say. Now, the key, though, is this subtraction, and that's what I want to point out to you guys. The reason you don't start with this original version and you go to the partial fraction decomposition version using getting this difference is you're going to see collapsing terms. Okay? So let me show you what I'm talking about, the collapsing terms now. So if we start with n is 2, we'll get 1 over 1 minus 1/2. This is when n equals what? 2. Okay? Now the next term happens when n is 3. Now when n is 3, we get what? 1/2 minus 1/3. Now, what do the terms look like when n is 4? That'll be 1 what? 1/3 minus 1/4. Okay. And we're going to go all the way up to, I might say, n equals big N minus 1. And big N minus 1 is going to give you big N minus 2 minus 1 over big N minus 1. That's the almost to the last term. And the last term is when n is big N, meaning 1 over n minus 1 minus 1 over n, I believe. No. Yeah, 1 over n. Okay. So we're looking at the terms of the series. N is 2, n is 3, n is 4, n is n minus 1, and then n is n because we start with n is 2, and we end with big N. That's the sequence of partial what? Sums we're talking about right here. Okay? You guys okay with that? Now, you said, okay, Mr. Judge, this is going to be the proverbial example of a telescoping series. It's a classic series you first look at in chapter 12 too. The terms will collapse because of the minus sign. So if I said to you, what are they really saying here? Do you guys see it? We can get rid of our parentheses here. Maybe not. We'll keep them for now. We got to study the pattern of what's happening here. And you say, well, what's the pattern? The second term, when n is 2, will cancel with the first term when n is 3. So you're really considering the first two terms here. Okay? We have some terms disappearing. Is that right? And that's what I'm kind of seeing at first happen. And then what happens next is the second term of the second, the second term of the second of n3 is going to cancel with the first term. And if I continue the pattern here, because maybe in the beginning we do have to see really what's happening here. Okay, this is an important detail. If I said to you, what would happen if n is 5 now? What starts to cancel? What's the pattern here? Well, we would get 1 what? N is 5, 1/4 minus 1/5. What's going to happen now again? This second term of the first pair will cancel with that first term of that second pair. And if I go back and look at n is 6 now, we're going to add this. That'll be 1/5 minus 1/6. If n is 6, as we look at those terms, what do we see going away? Yeah. And so now, going up to this n minus 1 term, and the n term. Let me move that here. Okay. I'll do one more. N is 7, so that becomes 1/6 minus 1/7. What do we see happening? Some more of this collapsing phenomena. So what's the pattern here? Well, nothing gets rid of that number 1, but what do you see really happening? Do you guys know? All the other terms are going away. Notice this, with the exception of what happens at the end here. See that 1/7? So what I'm going to remark to you guys is these terms go away with the exception of the last term. In other words, most of those terms have done what? They have collapsed. Is that right? They've collapsed here. So Sn is really 1 minus 1 over n. Okay? Because the terms have collapsed. When I use partial fraction decomposition and I rewrote that quotient, okay, instead of 1 over n times n minus 1, I get 1 over n minus 1 minus 1 over n. And so what that does for us now is really, it gives us a nice sequence for us to take the limit now. So remember what I gave you guys last time. We're going to look at the limit as n goes to infinity of the sequence of partial sums. And this n is now a capital N, by the way. And we could have kept it lowercase, but I didn't want to confuse you on that first example. But what's this limit equal? Isn't that 1? In other words, this is that sum, that's S. Remember we gave you that fact? What do you want to see? If the limit as n goes to infinity, your sequence of partial sums is some finite value S, then the series, what? Converges. And the series is equal to that S. So what we have shown is that the series converges, and it converges to the value 1. So what we can say now is, guess what? Series that we started with, 1 over n times n minus 1 is equal to the number 1. We have, in fact, convergence here. Okay? And that's your first example of what I call the sequence of partial what? Sums. It's a telescoping series where most of the terms, in fact, almost all the terms, with the exception of two terms, they just disappear. They're gone. Okay, do you guys see the point? That's a classic telescoping series. All right. On my worksheet, I guess this is number, I did this. This is like number 9 on the worksheet, by the way. So there's number 9. Let's look at another one. This is number 10 on the worksheet. Start at 1, end at infinity. We now have 2 over n squared plus 4n plus 3. Again, notice that this particular series is not what? It's not geometric. And again, you might say, well, why? Well, does it look like this? It's not of this form. Is that right? This is your geometric series. So this particular series is not geometric. So, okay, we can't use the fact from a geometric series we used last week. So then the question, what do you do? Well, the only thing you can do is consider the sequence of partial sums. And again, you don't have necessarily a situation that's going to give you anything other than a rational function where you want to use, again, what? PFD. What's PFD? Partial fraction decomposition. So use PFD, and I'll tell you what happens by PFD. The quotient 2 over n squared plus 4n plus 3 by that process becomes 1 over n plus 1 minus 1 over n plus 3. So, like before, the series is really going to be from 1 to infinity, 1 over n plus 1 minus 1 over n plus 3 now. So why is this nice? Because we're going to have that subtraction of terms now. Just like before, this is going to be a telescoping situation. Telescoping. Okay? So, okay, sequence partial sums, what does that look like? Well, we're going to say, okay, S big N is going to be sum from 1 to big N, 1 over n plus 1 minus 1 over n plus 3. So start looking at the terms, ladies and gentlemen. That's where you have to start. We got to look at the terms and then see which terms go away. But I want to give you guys a big hint here. The last example, you see this n and the n minus 1? Do you know what's going on? This is really the difference between a nth term and a prior term. Like n minus 1 and n, that index value differs by 2, really, right? N minus 1 is the prior value, n is the current value. So that differs by 2. In this example, you're going to see the effect here, where you got n plus 1 and n plus 3. So you got n plus 1, n plus 2, n plus 3. That's 3 terms you're going to have to see. So we're going to have to really take a closer look, is what I'm saying. It's not as simple as the first one. The first example is always the simplest one. This one is not as simple. So, okay, let's see what that looks like for us, right? So as we start to look at the terms, notice we're going to start with n as 1 here. We get, what do we get when n is 1? Isn't that 1/2 minus what? 1/4. You see my point? You got 1/2 and 1/4 now. They're not like prior terms. That's when n is 1. And then you're going to have what? When n equals 2. 1/3 minus what? 1/5 when n is 2. Plus, now n is 3. 1/4 minus what? 1/6. That's when n is 3. So let's really take a look at what's happening here. The negative 1/4 finally goes away with the positive 1/4, and that happened by looking at like the first 3 iterations. N is 1, n is 2, n is 3. Finally, something collapses. So that's what I'm getting at. We might have to look at another 3 terms. N is 4. And you say, what happens now? Well, that's going to be 1/5 minus 1/7 plus n is 5. 1/6 minus 1/8. And then n is 6. Let's take a close look. N is 6. That's 1/7 minus 1 what? 9th. So the next 3 terms. 4, 5, what else? 6. All right. So what's going on with the collapsing now? Do you guys see? We get rid, now, again, we get rid of the what? The second term and that first term. So the first term when n is 5, the last term when n is 2. The second term when n is 4, the first term when n is what? 6. So I want you guys to see initially 1/2 is never going to go away, and neither is 1/3. Would you guys agree with that? Those will never what? Go away. What else is going to stay? See these 2 terms? Take a look at this. This is meaningful. With that pair of terms, because they differ by 2, the first term is going to, sorry, that first pair, the second term stays. This is what I'm saying. The second term stays here, and the second term stays here. Is that true? Just in what you're looking at now, when you stop at 6. But we're going to go all the way now to this. We're going to look at n equal to n minus 1, and then n equal to n. What does that look like? Well, n minus 1, we're going to put back here. Plus 1, that's 1 over n. Sorry, wrong class. 1 over n over here. Minus 1 over n plus 2. And then, finally, 1 over n. That'll be 1 over n plus 1. Where are these indexed? Minus 1 over n plus 3. Okay? So we're just plugging in those values here in this difference. So I ended at n where I'm supposed to end, but I took the prior term as well. You say, why, Mr. Judge? Because what you guys see here, that's being left. This term is left, and this term is left. If I just focus now on that pattern, and since I went all the way to n, I do know from what happened prior, everything else what? Goes away. You see my point? That's how this is going to end. So what you really have is important. Sn will be 1/2 plus 1/3 minus 1 over n plus 2 minus 1 over n plus 3. Because all these other terms are going to go away. They're going to collapse because we took a look at the pattern that ended right here. All right. You guys okay with that? That's the key. That's what's going on with these telescoping series here. Okay? And so now the limit here, as you say, I have to look at the limit. Yes? As big N goes to infinity, Sn is the limit as n goes to infinity of 1/2 plus 1/3. Let's move it down. I guess we might fit. Minus 1 over the n plus 2 minus 1 over n plus 3. Where does that limit go to? Remember, this goes to 0, doesn't it? This goes to 0, so we converge to 1/2 plus 1/3. Okay? Let's actually do some arithmetic here. That's finite. 1/2 plus 1/3. You guys know what that gives you? It's 5/6. So this number is finite. Okay? Our series converges. And it converges to 5/6. So this is the infinite sum. It converges. It's not geometric. This equals 5/6. Sure enough, we have convergence. This is our very, very famous, another example of a telescoping series, okay? All right, now, let me try something else here. Let's give you guys another example of a telescoping series. This one, I think, is number 11 on the worksheet. The sum, 1 to infinity, natural log 1 plus 1 over n. Again, this is not geometric. You say, why is it not? Well, you can test it the way we did it last week, but it's not of this form, your geometric series. So, okay. Now, you might say, well, what do we have to do then? Well, the only thing we have is the sequence of partial sums. So consider that sequence of partial sums now. Okay, so Sn is the sum from 1 to n, natural log 1 plus 1 over n. But notice we don't have a way to see possibly a difference that this is telescoping. It's going to be telescoping, but let me show you guys why. You're going to use some algebra. You can't use partial fraction decomposition, can you? It's not a rational function. But by algebra and properties of logs, we know this is the natural log of n over n. Replace that number 1. Okay, replace 1 with what? See that n? N over n, and you say why? Because now I can add, meaning I have n plus 1 over n. And then by properties of logs, I'm using the quotient rule. Now, you say I can see that the sequence of partial sums is the natural log of n plus 1 minus the natural log. I can see how this is possibly going to be what? Telescoping. So we're going to have a telescoping, collapsing series again. And that's the whole idea. These first three are telescoping series. Okay, well, in that case, let's take a look at the terms now, right? So Sn, when n is 1, this is where we start. We get the natural log of 2 minus the natural log of 1 here, okay? Plus, now n is 2, okay? The natural log of 3 minus the natural log of 2 by just plugging in the values for n. Now remember, these terms differ, n and n plus 1, they differ by really one term. Like one value there, right? So I'm going to do a couple of more pairs here. Or, yeah, n is 3. You say when n is 3, we get natural log of what? 4 minus natural log of 3 now. Now let's look at when n is 4. You get natural log of 5 minus the natural log of 4 again. Okay. And I'm going to try to take a look now at what cancels, what goes away now. We're just at the fourth term. So what's starting to go away? Do you guys see? The first term and the what? Second term here. Is that right? Just with those pairs. The first term of that when n is 1 and the second term when n is 2. Those are consecutive values of n. And then what happens? Your n3 goes away. Is that right? And then what happens as well is that first term and the last term. So let's take a look at some more to see if we can see a pattern. This is when n is 5. We get natural log of 6 minus the natural log n is 5 minus the natural log of n is 5. Then we get natural log of 7 minus the natural log. This is when n is 6 of 6. Okay. And so this is going to tell us some more information. That what I'm starting to see, what are we starting to see? The second term again, and the what? Oops. Sorry. That first term in the first pair, and then the second term in that last pair. Natural log 5 is gone. Natural log 5 is gone. What is left, ladies and gentlemen, here? Yeah, you got natural log of 5, and that's negative. Natural log of 1, and it's negative. You got natural log of 7. This is really how the series ends. You say, what are you talking about? Okay. This is what I mean. When n is big N minus 1 and n is big N, what does that look like, ladies and gentlemen? Okay. Natural log of what? This is big N minus 1, so that's just big N. Is that right? So that's just big N minus natural log of big N minus 1 plus what? Natural log of big N, so that's N plus 1 minus natural log of what? Big N. So I want you guys to see that what's really happening is in this prior situation, meaning these two terms go away and that last term goes away. What's really staying is right here. And this is actually gone as well. Okay? As we continue with our ends. So your sequence of partial sums, this Sn now looks like the following. It's minus natural log of 1. Okay? This term is there. Everything else collapses, goes away. And you say plus the natural log of n plus 1. Now, isn't the natural log 1 0? So, ladies and gentlemen, your sequence of partial sums in closed form is just the natural log of n plus 1. So what that means is the limit as big N plus 1 goes to infinity is really the limit of what? What does that equal? Infinity. So as n gets big, what's the deal? Sn goes to infinity. What does that mean? The sequence of partial sums what? This means that the sequence of partial sums diverges, and so does this what? Series. The series also diverges. We write it down this way though, right? We can say it this way, symbolically, equals infinity, or just simply diverges. It's a pretty big deal, ladies and gentlemen. So the sequence of partial sums diverges, so does the series. And that is something that we want to observe as well. Number 11 here. Okay? There's your conclusion. Now, I'm going to give you guys an important fact because this is also a major idea in the section here. This last part is going to be the last major piece of chapter 12-2. Here's what I mean by that. I want you guys to know this fact. This is a very trivial fact. If a sequence converges, remember that? Sorry, if a series converges, then the limit of an equals 0. Okay? I'm going to start off with this fact. And let's look at the proof of this. Your proof is that we want to assume that we have convergence of the series. Well, if we have convergence of the series, in other words, the sequence of partial sums converges. Okay? And that's the Sn sequence. In other words, if we let Sn be the sum of the first n terms, which is what it is by definition, then we also know that the prior term, Sn minus 1, is really defined to be a1 plus a2 up to an minus 1. Now, I'm going to do something here for you guys. I'm going to do what I did in the prior demonstration. So we're going to compare those two. We know that the sequence of partial sums converges. Now, what I'm going to do here is we're going to look at the difference between Sn and Sn minus 1, and notice that's just An. Because if I take the difference of these two, we have collapsing. And we're just left with the what? With this term. Okay, it's collapsing, that difference. Okay, so then if we take the limit of an, which is the limit really of Sn minus 1, by properties of limits, that's the limit of Sn minus the limit of Sn minus 1, well, they both converge to the same place, S. And then that limit equals 0. Okay, so this is an important fact of the section. However, let me say this to you guys. This particular fact, which is important, is kind of useless in a direct sense. That when you have convergence of a series, then the limit of an is 0. And it's kind of it's kind of useless in some ways. So this conditional that we're looking at is really kind of not a very useful piece of information in terms of the series. But notice I wrote this as a conditional. So what does that even mean as a conditional? Well, the value of this statement does not apply to what you're looking at here. It's not very valuable to say that when you have a series that converges, we know the limit of an equals 0. Not very valuable. But what is valuable is this statement here. Because if you guys recall, every conditional is equivalent to its contrapositive. This is gold. The contrapositive statement, okay? And that's kind of reading it really backwards. That's if not Q, then not P. This is if P, then Q. Over here, if not Q, then not P. It's called the contrapositive. This is the gold part. And the thing about contrapositives, if you ever prove that a conditional is valid, then the contrapositive is valid because they're really equivalent statements logically. Okay? So you see some of this stuff in calculus courses, you see it in geometry, and then you might say, well, what in the world are they really saying here? You know, what are they really telling us? Well, this is what this contrapositive statement means. We're going to negate the conclusion over here. I got to negate this limit an equal to 0. You say, well, how do I negate it? Well, I'm going to say, if the limit of an is not 0, then what can we say? Right? This is negating Q, then we can guarantee negation of P. What is this negation of P? And I have to say, or does not exist. So either the limit is 0 or the limit, I have to put this part, or does not exist. Okay. That's an important detail. That's the contrapositive. Then what could we say about the series then? Well, what's that negated statement? Negate P. What's the negation of convergence? It's divergence. Okay? So we have to negate convergence of the series. Then we can say the series diverges. This, ladies and gentlemen, is gold. Do you guys know why this is gold? This gives you what we call the test for divergence. The divergence test for short. Okay, divergence test. Test for what? Divergence. This is what we care about. So that first statement is really, it's a valid statement, but we actually use the contrapositive. Okay, now you might say, well, how do we use this then? Well, example would be number 12, which is looking at the limit from 1 to infinity. Okay, you got m plus 1 squared over n plus 2. We got to check, is this thing, does this converge or does it diverge? Converge or diverge, okay? All right. This over here is an. An equals m plus 1 squared over n plus 2. What this means is I got n squared plus 2n plus 1 by using FOIL in the numerator, and I got n squared plus what? 2n. You guys good with that one? You guys see my point? Okay. Now, what's the limit of an as n goes to infinity? Well, that's the limit as n goes to infinity of what? N squared plus 2n plus 1 over n squared plus 2n. Do you guys know what this limit equals? Use calculus 1 or calculus 2. What's this limit going to be? That limit is 1. Is that true? No? How do we know that limit is actually 1? Well, if I divide every term by the highest power in the denominator, n squared, you guys remember this from calculus 1? Don't I get the limit 1 plus 2 over n plus 1 over n squared over 1 plus 2 over n. So I can actually use calculus 1 or calculus 2. And this limit going to be, because this term, this goes to what? 0, 0, 0. You got 1 over 1 plus 0 over 1 plus 0. Isn't that 1? Now, that limit is 1, ladies and gentlemen. Why is that so important? It's not equal to what? 0. Because the number 1 is not 0. What do we know? If the limit is not 0, or the limit does not exist, what can we say? The series diverges. This is called the test for what? Divergence. So we know that this series what? Diverges. And very often we want to say why? By the divergence test. Here's an example of a divergent what? Series. So this thing, we want to get that tattoo. It's a test for divergence. Now, on your test and final, I always give you guys that cheat sheet. I'll show you guys probably tomorrow the cheat sheet. And it's on that cheat sheet, test for divergence. But you guys really want to know that this statement I just showed you guys is completely useless on its own. So a lot of times students just look at this. They want to read it backwards. They want to say, oh, if the limit of an is 0, then the series kind of converges. Nope, it doesn't. You can only use the contrapositive statement. And that contrapositive statement is if the limit is not 0 or the limit does not exist, because that's the negation, then the series diverges. That's the negation of P. Very, very powerful logic here in math. And that's kind of stuff you learn like in a geometry course, by the way, in case you guys didn't know. Anybody ever have a good geometry course? No? All right, let's look at number 13. The sum 1 to infinity n over n plus 5, okay? Again, here's an example of this. This is an. Notice you can't use partial fraction decomposition here. Okay? It's not geometric. So let's look at the limit of an, which is the limit as n goes to infinity, n over n plus 5. Do you guys know what that limit is? That's 1, and then that does not equal 0. What do we know? This what? Diverges. And we could put something like this, equals infinity. That means diverges, and we'll say by the divergence test. Okay? How do we know this is 1? Same logic. Divide every term by what? N. That's the limit. N goes to infinity. 1 over 1 plus 5 over n, which equals 1. So in case you guys were wondering about that, you said, how could that be? Go back to calculus 1. Or look at L'Hopital's rule. Calculus 2. This could be done by L'Hopital's rule. We've seen that as well. All right. 14. Sum n squared over n squared minus 1. And I believe here we got to start at 2. Can't start at 1. We can't divide by 0. Okay. This is my an. It's not geometric. I don't believe we can write this as a difference using partial fraction decomposition. So I'm going to look at the limit as n goes to infinity of an. And then these are examples, ladies and gentlemen, of really tests for divergence. Isn't that limit also 1? You guys know what I'm saying? And that limit is not what? 0. So this series, what? That diverges by your test for divergence. Okay? Okay. Let's look at this next series here. 15. Again, we're going to call this what? AN. So AN is going to be the sum 1 to infinity. I'm sorry. AN is going to be natural log of n over 2n plus 5. This is not geometric. You can't use partial fraction decomposition. We're going to investigate the limit as n goes to infinity of an, which will be the limit n goes to infinity of the natural log of n over 2n plus 5. Okay. Does anybody happen to know what this is? Let's look at the details. What do we know about n to the 2n plus 5? Where does that go to as n goes to infinity? You guys know what that goes to? Does that go to 1/2? You could use calculus 1 or calculus 2. So that means the natural log of n over 2n plus 5 goes to a nice continuous curve like the natural log. Sorry. This goes to natural log of 1/2. What do you guys know about the natural log of 1/2? It's not equal to 0. Since it's not 0, what do we know? You just showed as n goes to infinity, an goes to the natural log of 1/2, which is not 0. That means the series what? Diverges by the what? Test for divergence. Okay, and then finally, 16. What about this? The inverse tangent of n. It's not geometric. You can't use partial fraction decomposition. So we know an is the inverse tangent. I'm going to look at the test for divergence now. Do I happen to know what's the limit of the inverse tangent? Is that pi over what? Is that pi over 2? Isn't that not equal to 0? So the limit here of an, again, is not 0. That means the series diverges by the what? Test for what? Divergence. And we can kind of write it this way. Just say that that thing equals what? infinity maybe. Okay, that's the symbolism for divergence. So, ladies and gentlemen, I'm looking at the first worksheet with series. Those are really the things that you care about, in all honesty, of the section. Now, there's some other little details that I didn't give you yet, but I will in the future. I'm just going to give you guys a fact that we'll see tomorrow. Here's a fact. This series here, from 1 to n, diverges. Okay, I'm going to just give it to you guys as a fact for the moment. And we'll see tomorrow why that diverges. But this is the very famous harmonic series. So I'm going to define that for you guys today. The harmonic series. Because this series shows up in math and science all the time. It's the very famous harmonic series, and the harmonic series is a series that diverges. Okay, now you might say it diverges. Yes. But let me show you something. You might say, but the limit, if I call this an, of an equals the limit of 1 over n, what's the story here? What do we know? This limit equals what? 0. Is that true? So I'm going to put this in red. What does it mean for an going to 0 as n goes to infinity? What does this mean if the limit of an goes to 0 as n goes to infinity? You know what this means? It means nothing. Okay? It means nothing. This is what's going to confuse some people. It's the logic, it's the language. That just because you have the limit of an equal to 0, does that mean the series diverges? Say no. Why? Because what do we have to have? The limit of an could not be 0 or does not exist. Then we conclude the series diverges. Oh, so if the limit of an equals 0, does that mean the series converges? No, it doesn't. Because I said to you guys, we'll prove tomorrow that the harmonic series limit of an equals 0, but it's a very famous divergent series. So just because you have an equal to 0 as n goes to infinity or an approaches 0, this does not mean anything. People are trying to read that original statement I started off with backwards. You can't read it backwards in the sense that if you're trying to say, okay, if the limit an equals 0, then, oh, I know, then the series what? Converges. The answer is no. That's not the case. This is called the inverse of a conditional, and the inverses are not, ladies and gentlemen, the inverse is not valid. Okay, it's not valid in this case. That has to be proven to be valid, but it's not. So in other words, P arrow Q is not equivalent to Q arrow P. That's what I mean by reading backwards. So if your limit of an equals 0, then it doesn't mean the series diverges. And let's write that down, okay? Because that's where people are going to make a mistake. If the limit of an equals 0, I'll put it in red. Okay, then the series can either converge or it can what? Diverge. We don't know. What I mean by that is you're going to probably have to use some other test because there's no guarantee the series converges. It may, or it can diverge. We just don't know. So don't read that statement backwards. Okay? Conditionals is equivalent to the contrapositive, but it is not equivalent to the inverse. This is called the inverse of a conditional. All right, you guys okay with that? And now that's going to conclude chapter 12 too. So in your homework, the assignment portion, work on the questions in what? 12.2. Tomorrow we're going to start the what? We're going to do integral test and limit comparison test. So, you might want to take a look at those tomorrow as well. All right? But look at your series. So, ladies and gentlemen, welcome back. I'll see you tomorrow. I hope you guys enjoyed this. It's not so bad. And notice that we have here negative 3 to the nth power. So this numerator is what we describe as an alternating mechanism. What I described as that. And so what we want to investigate now is the absolute value of this statement. We're going to take the limit of the absolute value. We're really making all the terms positive. So using properties of absolute value now. So that's going to be negative 3 to the n in absolute value divided by n factorial in absolute value. Okay, so that's going to give us the absolute value of negative 3 to the n, which is really 3 to the n, that numerator, over n factorial. And the reason we can remove the absolute value sign for n factorial is because n is a natural number, right? N, which means our n is positive. Alrighty. So we're going to now look at the limit here of the absolute value, which will be the limit of 3 to the n over n factorial as n goes to infinity now. Okay. Now, let's really take a closer look here to the terms of what this is by definition. So we're going to say this here is defined to be, if we look at these terms, algebraically speaking, 3 to the n is 3 times 3 times 3. We have n of these. N factorial is n minus 1, n minus 2, down to 2 times 1 here. Okay. So I'm going to separate here. I want you guys to focus on really what? You got this 3 to the n. Let's look at some details here. I'm going to look at the details this way. Let me change the terms. And put it this way. 1 times 2 times 3 all the way up to n minus 1 times n. And every one of these numerators here is really 3. So I'm just writing my factorial backwards. Okay? And then I want you to see that this is going to be smaller than 3 times 1, 3 times 2, times 3 times n, and starting at 2 now. Okay, so you might say we have what over here? Those terms, and then you got this last term here, 3 to the n. So this portion is now going to become 27 now over 2 to the n. Okay. And so this sequence here is smaller in absolute value than 27 over 2 to the n. So we know that this portion will go to 0 as n goes to infinity. So we're looking at this going to 0 as n goes to infinity. And so because that goes to 0, this is a smaller, this is the bigger sequence goes to 0 as n goes to infinity. So what that means is that smaller goes to 0 as well. So the absolute value of an goes to 0 as n goes to infinity, and then that means now an goes to 0 as n goes to infinity because of the theorem that we wrote down earlier, which is that if the series in absolute value goes to 0 as n goes to infinity, then an goes to 0 as n goes to infinity. So this converges here. And this is a different kind of logic for you than calculus 1 or calculus 2. So it's in calculus 2 here. Okay. Now, similarly here with n factorial and 2 to the n now, let's write this one down. What this one actually means as well. So I'm going to write it the same way. N factorial, by definition, I write it, we'll write it backwards so you guys can see the logic. So this here is 1 times 2 times 3 all the way up to n minus 1 times n. That's my numerator. And then I have, under every one of those terms, 2. I have n of these terms. Okay. So we're going to focus on now here these terms and know that this is going to be greater than or equal than 1/2 times n over 2, which makes this portion here n over 4. So let's take a look. An is greater than or equal to n over 4 now. And this is for n greater than 1. Okay, so we're going to say this here. As n goes to infinity, the smaller sequence goes to infinity. So we're looking at the smaller sequence here going to infinity. So what that implies now is that the bigger sequence also goes to infinity as n gets big. So we have the sequence diverging here. So this sequence will diverge. So the smaller sequence gets big without bound. That implies that the larger sequence gets big. And that larger sequence is an. Got divergence. And then finally, n squared minus 1 for number 20. We look at the limit now. As n goes to infinity, n squared minus n is an indeterminate difference. So we're going to get to use here algebra, calculus 1. So factor out your n, and we get n minus 1 here. So we'll have the limit as n goes to infinity, n times n minus 1, which we now get by the product rule of limits, infinity times infinity, which gives you infinity. So here's what this means, I guess. We can say this. An goes to infinity as n gets big, which again now means your sequence simply diverges here. Okay. All right, I will send this to you guys. I hope you guys enjoyed this demonstration. I finished the worksheet for you.